Hey there, Keys Precalculus. We are going to go over section 7.6, the inverse of a square matrix. We started it in class. We did a couple of examples on how to show if two matrices are inverses of each other, but we haven't really finished learning how to find the inverse of a matrix. So we're going to look at example 2. Now, before we do that, though, I wanted to remind you this identity matrix I, it is the matrix here that I'm hoping you can see that I'm circling. It's the red one here, 1, 0, 0, 1. It's going to be the same order of the matrix we're looking at. So if it's a 2 by 2, then it'll be 2 by 2. If it's a 3 by 3, it'll be 3 by 3. But this is the identity matrix. And when you multiply a matrix times its inverse, you're going to get the identity matrix. And we're going to use this to figure out how to find the inverse of a matrix. So we're going to start with A. We're going to say A times its inverse equals the identity matrix, right? Well, we're going to let the A to the negative 1, our inverse matrix, we're going to call it X. And it's going to be X1, X11, X12, X21, X22, or it's going to be its elements. So we're going to substitute the A, what it is, the matrix for A in black, and the matrix for its inverse, which we don't know, in blue, and that's going to equal the identity matrix. Again, because we multiply a number times its inverse, its multiplicative inverse, we get the identity, its identity, or the multiplicative identity. Or if we take a matrix and we multiply it by its inverse matrix, we're going to get the identity matrix. Okay, so we're going to go ahead and multiply the black and the blue matrices together, and you do that by using dot products, and we end up with 1x11 plus 4x21 in first the top left in the 1 place, and then 1x12 plus 4x22 in the row 1 column 2 place, and then the same thing for the other elements. You can see that, and we're going to set it up here to the identity matrix of 1, 0, 0, 1, because that's what it equals. Then what we can do is, because two matrices, if two matrices are equal, their elements are equal, and so we've got this black, this multiplied matrix here, this product matrix is equivalent to the identity matrix. We can set up each element as being equivalent to each other. So I underline, like the green one is going to be equivalent to the green one, and I wrote it here. And then the orange one is equivalent to the orange one, which I wrote here. So you can see that row 1, column 1 is equal to row 1, column 1 here. Row 2, column 1 is equal to row 2, column 2 here. And so if I do that, I also have equivalent, I have like terms. So I can set up two separate systems of equations. And when I solve those two sets of equations, either by substitution or elimination, I get the first element, x11 is negative 3, x21 is 1, x12 is negative 4, and x22 is 1. So I'm going to write that out here in blue as negative 3, negative 4, and 1, 1. That is my x. I've solved for x, which is also the inverse matrix of the original matrix A. We did all of this in class, but we didn't check it, so we're going to do that now. Okay, so to check your work, you would take the original matrix and you multiply it by its inverse to see if you get the identity. And when you do the dot product and you multiply it all out, you see that we do get the identity matrix. So A times A to the negative 1 is the identity matrix. Therefore, it seems like they're inverses of each other, but we're not finished. We also have to check the other way around. We have to check A to the negative 1 times A. And when I do that and follow the dot, use the dot product, when I multiply those two matrices together, I also get the identity matrix. So now I have checked, I've proven that negative 3, negative 4, 1, 1 is the inverse matrix of the matrix 1, 4, negative 1, negative 3. That's a lot of writing. So I'm going to show you an easier way to do this now. We started to go over that easier way in class. I'd like to finish it here and go through it a little more slowly. So again, I put up here on the board the original matrix A. And when we went through and found its dot product with X, with the matrix X, we got these two systems right here. Now, if I take these systems and I write an augmented matrix for each one, then I'm going to get 1, 4, negative 1, negative 3, or 1, 4 equals 1, and negative 1, negative 3 equals 0. And 1, 4 equals 1, and negative 1, negative 3 equals 1. If you'll notice this, if you'll notice the coefficient matrix for each one of these, right here, this coefficient matrix is the same as this coefficient matrix right here, isn't it? Which is actually matrix A. So instead of going through and putting all my X's and doing two separate systems and solving them separately, I can create a doubly augmented matrix with A and the identity matrix, I here, and use my row operations and solve for everything at once. And then I don't have to worry about variables. I don't have to worry about solving two separate systems. I can just do everything at once. And so we're going to do that here. Now what you can see is I've taken my coefficient matrices, the ones that are highlighted in yellow, and I rewrote them down here, right down here in black, as 1, 4, negative 1, 3. And then I augmented it, or doubly augmented it, with the 1, 0 from the left one and the 0, 1 from the right one. So now I have one matrix I can do row operations on to see if I can solve for my inverse matrix. And the way I'm going to do it is I'm going to turn this black side into a reduced row echelon matrix, or I'm going to turn the black side into the identity matrix, and then whatever this red side ends up being is going to be my inverse of the original 1, 4, negative 1, negative 3, or my original A matrix. Okay, so let's go ahead and do that. Now, I want y'all to pay attention to this, because some of you are missing how to do row operations properly. Also, you're being messy, and so you've got your matrices all over the paper, and it's really hard to follow. So let's work on trying to get everything in a very systematic order. I'm going to try to do that for you here as well. And I'd like you to try to set up your papers this way as well. So what we're going to do is we're going to look at this matrix, and we want to turn our black side, the left side, into the identity matrix, 1, 0, 0, 1. So we have to do row operations on it. So when I look at this, I see that I need my top left element, my row 1, column 1 element is already 1. But I need to make the row 2, column 1 element 0. So in order to do that, I can add row 1 plus row 2 to get a new row 2. When I do this, I do not want to replace my first row. I only want to replace my second row. So I'm going to write beside the second row what I'm going to do to it in order to change it. And when I do that, I'm going to, and I'm going to go straight to just black and blue right now. I'm not going to do anything with my top row. I'm going to leave it the way it is. So when I leave it alone in this case, I'm going to leave it the color black. Now I'm going to change to the blue because I'm changing my second row. And I'm doing that by adding row 1 to row 2 and putting my new answer on row 2. So 1 plus negative 1 gives 0, and 4 plus negative 3 gives me 1, and then 1 plus 0 gives me 1, and 0 plus 1 gives me 1. So I have rewritten my second row by adding the first row to it and writing the answer down in the second row. And as you can see, the second row is what it needs to be. It's a 0 and a 1 on the left side. But the top row is a 1 and a 4, and I don't want that 4 to be 4. I want it to be 0. So I need to change it. How am I going to do that? Well, I can take my second row and I can multiply it by a -4. So if I say -4 times row 2, and I add it to row 1, then I'm going to get a new row 1. But in this case, I'm not going to change my row 2, so I'm going to make that one black. So right here, I'm going to rewrite my row 2 because I'm not going to change it. 0, 1, and then 1, 1. But I am going to change my row 1. So I'm going to come over here and I'm going to say this row 2 here times -4 plus 1. So -4 times 0 is 0 plus 1 is 1. I'm going to put that answer on my new row 1. And then I'm going to come back to the middle one that I just worked with. And I'm going to say -4 times this one and add it to that 4. And when I do that, I get 0, and I'm going to put that new answer here. But I also have to do it with the right side of the augmented matrix. So -4 times 1 is -4, plus 1 is 3, or -3, sorry. And then -4 times 1 plus 0 is -4. So now do you see how my left side is 1, 0, 0, 1, and my right side is -3, -4, 1, 1. And that is my identity matrix, and it's the same thing that I got in my other answer when I solved it with systems. Recall right here, -3, -4, and 1, 1, this blue one, equals x, which is the inverse of A. But creating a doubly augmented matrix and solving it with row operations is much simpler. It takes up less space, and you're less likely to make a mistake. All right? So here I could say that a to the -1 is equivalent to -3, -4, 1, and 1. And if you would check it the same way. You would multiply a times a to the -1 to see if you get identity, and the a to the -1 times a to see if you get the identity. Not every square matrix is invertible. We're going to do a couple of examples to show you one that is and one that isn't. Okay? Okay, so example 3 on page 522 says to find the inverse of matrix A. Matrix A equals, let me write this down. Matrix A equals 1, -1, 0, 1, 0, -1, 6, -2, -3. So we're going to start this process by rewriting it as an doubly augmented matrix, or triply now, an augmented matrix with its identity matrix of the same order. So I'm going to rewrite this 1, 0, -1, 6, -2. And then I'm going to augment it with 1, 0, 0, 0, 1, 0, and 0, 0, 1. And perform elementary row operations to turn this left side of the matrix into an identity, and the right side will be the inverse of A. And that's how I'm going to find the inverse of A. When I do this, I'm going to write beside each row what operations I'm going to do to it in order to change it. I'm not going to write anything on row 1 here, on this top row, because I don't need to change it yet. My first, my element in my row 1, column 1 is a 1. I want to leave it right now. But I do need to change the first element in row 2. I want to make it a 0. So I like to add instead of subtract. It helps me keep track of things better. So instead of saying row 1 minus row 2, I'm going to say -1 times row 1. And I'm going to add row 2 to it. And when I do that, I'm going to get the same result. But also, I can, at the same time, I can change row 3. I can take -6 times row 1, and I can add it to row 3 to make that first element a 0 as well. Now, I can do this both with row 1s because I'm not changing row 1. I'm only changing row 2 and row 3. Row 1 is going to stay the same. So I'm going to rewrite my next matrix right next to it, and I'm going to only change row 2 and row 3. So So I'm going to write row 1 first. 1, negative 1, 0, augmented with 1, 0, 0 here. And now I'm going to do my blue, and I'm going to say this row 1, the middle matrix that I'm working with here, middle row 1 times negative 1 plus 1, that's going to give me 0 in my row 2, column 1 space. So I'm going to write a 0 right here. And then when I take negative 1 and I multiply it by negative 1, I get positive 1 plus 0, gives me a positive 1 in the second space. And then a negative 1 times 0 is nothing, plus 1, it gives me a negative 1. And then negative 1 times 1 is negative 1 plus 0 is negative 1 right here. Negative 1 times 0 is 0 plus 1 is 1. And then 0 plus 0 is 0. So I've got my new row 2 by taking the row 1, multiplying it by negative 1, and then adding it to row 2. Now I'm going to get my new row 3 by taking this original, this matrix right here, I'm going to take row 1, and I'm going to multiply it by negative 6 and add it to row 3. So negative 6 plus 6 gives me 0. And then I'm going to look at this one right here. Negative 6 times negative 1 is positive 6 plus negative 2 is 4. And then I'm going to look at this last one here. A negative 6 times 0 is 0 plus negative 3 is negative 3. Then I've also got to do my augmented side. So negative 6 times 1 is negative 6 plus 0 gives me negative 6. I'll do that one. Now I'm going to do this one. Negative 6 times 0 is 0 plus 0 is 0. And then negative 6 times 0 again is 0 plus 1 is 1. So now I have a brand new matrix that I've created using row operations. But I'm not done. This element right here is 1. And this one is 1, but I need this one to become a 0. So I have to perform row operations again to make that a 0. I'm going to, just for neatness sake, and because I don't have room on the right, I'm going to rewrite this newly augmented matrix over here on the left. So as you can see, I have simply rewritten the augmented matrix up here down on the left side, so I can start working with it and not get confused, and I can write out what I'm performing to the right of it and put my new matrix to the left of it and still have room for it. So the first thing I'm going to do is I know that I need to change this 4 right here into a 0. And if I were to use row 1 to do it, then I would change this 0 by adding something to it, and I don't want to do that. So I have to use row 2. So in order to change this 4 into a 0, I need to take row 2 and multiply it by negative 4, and I'm going to add it to row 3 to get a new row 3, a 0 in that place. But at the same time, I can change this. I need this negative 1 to become a 0. And I can do that by just simply taking row 2 and adding it to row 1 and changing what row 1 is. So if I take row 2 and I add it to row 1, I'm going to change this second term into a 0. Okay, and what I'm going to write out here is I'm going to put in black the middle row because I'm not changing it. I'm not doing anything with the middle row, so I'm going to leave it as 0, 1, negative 1, augmented with negative 1, 1, 0. Now, when I do my row operations, I'll just do the top one first. I can take 0 plus 1 and I get 1. Okay, and then I'm going to say 1 plus negative 1, which gives me 0 because I just added up. And then negative 1 plus 0 gives me negative 1. But I got to do the same thing with the right side. Negative 1 plus 1 is 0. 1 plus 0 is 1, and 0 plus 0 is 0. So do you see how we got this top row? Now I'm going to do the bottom row. I'm going to add negative 4 times row 1 here in the middle. It's not row 1, I meant to say row 2.
I'm putting an arrow to it. So negative 4 times row 2, and I'm going to add it to row 3 to get my new elements. So 0 times negative 4 plus 0 is 0. And then here, negative 4 times 1 is negative 4 plus 4. That gives me the 0 that I want. And then negative 4 times negative 1 is 4. And 4 plus negative 3 is a 1. Oh goodness, that's what I want it to be. This is working out very nicely. They don't always, but this one is. Okay, now I'm going to take negative 4 times row 2, which gives me negative 4 times negative 1 is positive 4, plus a negative 6 is going to end up giving me a negative 2 in that spot. Whoops, wrong place. Sorry about that. All right, and then I'm going to take negative 4 times 1, it makes it negative 4, and I'm going to add it to 0 to get negative 4. And then I'm going to take negative 4 times 0, which is 0, and add it to 1 to give me a 1. So now I have almost everything done. Not quite, because I still need to make zeros in every place on the left except for in the main diagonal. But I'm almost there. What do I need to do? I need to turn this number right here, the third element on the first row, into a 0. Now, if I do that, I can't add the second row to it, because if I do that, it's going to change this second element, which is already a 0, into something that's not. But I could take my row 3 and I could add it to row 1. So if I take row 3 and I add it to row 1, I should be able to turn this third element into a 0. But then I also need to turn this third element and the second row into a 0. And how am I going to do that? Well, I can also add row 3 to row 2 to turn that third element into a 0. Okay, so when I do that, let me get my black over here, I am not changing my third row this time. So I'm going to leave it as 0, 0, 1. It is perfect the way it is. I don't need to change it at all. Negative 2, negative 4, and 1. But I do need to change my first and second row. So let's do the first one first. I'm going to take row 3. I don't have to multiply it by anything. I can just take its elements and add it to row 1. So 0 plus 1 is 1. 0 plus 0 is 0. And 1 plus negative 1 is also 0. But then I've got to do my augmented side. So negative 2 plus 0 is negative 2. Negative 4 plus 1 is negative 3. And then 1 plus 0 is 1. So I end up with a negative 2, negative 3, 1 in the top. Now I've got to do the second row. So I'm going to take the third row again, and I haven't changed it, but I'm going to add it to the second row. So 0 plus 0 is 0. That gives me what I want. 0 plus 1 is 1. That also gives me what I want. And 1 plus negative 1 is 0. That gives me what I want. But I got to do the augmented part. So negative 2 plus negative 1 is negative 3. Negative 4 plus 1 is also negative 3. And 1 plus 0 is 1. So, oh goodness, I made it an arrow. Huh, that's funny. All right, so this right side now, or first off, the left side of this last matrix is an identity matrix, which I wanted it to be. And as a result, this right side has become my new inverse matrix. So it's the inverse of A. So what I can say now is A to the negative 1 is equal to negative 2, negative 3, 1, negative 3, negative 3, 1, and negative 2, negative 4, 1. That is my inverse matrix. In order to check it, I need to multiply A times A to the negative 1 to see if I get I. And if I do, that part is half checked. And then I have to multiply the inverse of A times A to see if I still get I. And if I do, if they both check out, then I've done my work and everything's correct.
Not every square matrix is invertible. And we're going to do an example. This is example 4 to show you one that's not. So if we let B equal 1, 2, 0, 3, negative 1, 2, and negative 2, 3, 2, negative 2, I'm going to rewrite it as an augmented matrix with an identity matrix of the same order. So 1, 2, 0, 1, 0, 0, and then 3, negative 1, 2, 0, 1, 0, and negative 2, 3, negative 2, 0, 0, 1. Now I want you to practice doing row operations on this and get it down as far as you can, and then come back. So pause your video, do the row operations, and then come back and see if it's the same thing that I've got.
If you worked through this and you've gotten down to what I have here at the bottom of the screen, or in the middle of the screen, with a 0, 0, 0 augmented to negative 1, 1, 1, you can see that this left side, it's going to be impossible to make it the identity matrix because I've zeroed out the bottom row. There's nothing else I can do to it. So when it gets to a situation like this where I've zeroed out a row, it is not possible, and therefore it is not invertible. So I probably should have said saying not possible. I will say it's not invertible. I cannot find the inverse of this row. I think I spelled that correctly. Not 100% sure. Yep, I think I did. Okay, so it's not invertible. So you sometimes are going to run into situations like this. Now we're going to do one more example on how to use the inverse matrix to solve systems of equations. So this is just another way to use a matrix to solve a system of equations. So when we look at example 6 on page, I think it's 520, 524, and then we're going to talk about the determinant of a matrix. There's actually a simpler way to find the inverse of a 2 by 2 matrix than to go through row operations. But we'll do that in a minute after we learn how to use this to solve systems. Example 6 says to solve this system equations, use an inverse matrix to solve the system. So the first thing I'm going to do to solve this is I'm going to rewrite it as a coefficient matrix times a column matrix equal to another column matrix. So the coefficients of the left side of this equation are 2, 3, and 1, and 3, 3, and 1, and 2, 4, and 1. I hope you can see that. And that's my coefficient matrix. I'm going to use it to multiply by the column variable matrix of x, y, and z. And when I multiply those two together, I get 2x plus 3y plus z, which is the top row. And then I get 3x plus 3y plus z, that would be the middle row, and 2x plus 4y plus z, that's the bottom row. I get a dot product. And then that equals the column row of my constants, negative 1, 1, and 2. So I've just rewritten the system of equations as a multiplication of two matrices, or a coefficient matrix times a column matrix equal another column matrix. I'm going to call this coefficient matrix A. I'm going to call this X, and I'm going to call this B. Now, over here, AX equals B. I'm solving for X. So in order to solve for X, I have to multiply both sides by the inverse matrix. So negative 1A times X equals A to the negative 1 times B. Because I've done the same thing to both sides, these cancel each other out. And then I'm left with A is the inverse matrix of A times B. And if I can find what the inverse matrix of A is and multiply it by B, then I have solved for X. And so that's exactly what I'm going to do. I am going to find the inverse of matrix A. Or actually, you're going to do it. So I want you to pause the video and set up what you think would be the first step, and then check back and see if you've done the same thing that I've done. Did you set up an augmented matrix with the coefficient matrix on the left side and the identity matrix on the right side of the same order? Because that's what your step 1 is. And now the next steps are you're going to perform row operations to turn the left side of this matrix into the identity matrix, and the right side is going to end up being the inverse of A, the inverse of matrix A. So I want you to pause the video. I want you to work out your row operations and then come back and see if you have the same answer as I do.
So come back and have you checked, or come back, pause the video and look at it now and see if you did the same thing I did. But before you do that, I want to show you up here, I made a mistake. I did not transfer my negative sign originally to this column matrix. It should be a -2, because it's a -2 here. That is one of my biggest errors when I do these, is I sometimes write things down, I copy them down wrong. And I find that that's also a big student error. Make sure you're very careful when you copy things down that you get them correct. Okay? So go ahead and pause the video again and study what I have compared to what you have. If you notice, though, from this second matrix to the third one, I want to show you what I did. I first took row 2, the row 2 in this second matrix, and I added it to row 1 to get a new green row 1. And then I switched row 2 and row 3. I just switched their order right here because row 3 is in the order that row 2 needs to be in. It's already in that order, and it would be too hard for me to change it otherwise. So you can change rows. That's part of the row operation. And when you do that, when you multiply it all down, you will see that you get this identity matrix here on the left side, and on the right side here you're going to get the inverse of A, the inverse matrix, or the inverse of matrix A. So the inverse of matrix A equals -1, 1, 0, -1, 0, 1, 6, -2, -3. And what we're going to do now is we are going to set that, we're going to put it right back into this equation right up here. Okay, we're going to rewrite it this way. And I'm going to do that over here by saying x equals, but I'm going to leave that off for now. We'll put that on the end. The inverse of A times B. I'm going to multiply that out now. So I'm going to take the inverse of A, which is -1, 1, 0, -1, 0, 1, and 6, -2, -3. Did I copy all of those things down correctly? Hope so. And I'm going to multiply it by matrix B up here, which is this one that I'm circling. So I'm going to multiply it by that column matrix of -1, 1, -2. Okay. And when I do the dot product, that's going to give me my XYZ matrix up here. But we're not going to go there yet. We'll add that in later. So when I multiply these two together, I'm going to get a dot product. -1 times -1 is 1. And then 1 times 1 is 1. I'm multiplying, row 1 on the left with column 1 on the right. And then 0 times -2 is 0. Okay? And then I'm going to take row 2 here, and I'm going to multiply it by the column. So -1 times -1 also gives me a 1. 0 times 1 gives me a 0. And then 1 times -2 gives me a -2. And then 6, so I'm going to do the third row by the column now. 6 times -1 gives me -6. -2 times 1 gives me -2. And then -3 times -2 gives me a +6. So when I simplify that, I end up getting 1 plus 1 is 2. 1 plus 0 plus negative 2 is negative 1. And then negative 6 and positive 6 is 0. When I add it to the negative 2, I get negative 2. So this should be my solution, which is my x, y, and z matrix. In other words, the inverse of matrix A times matrix B gives me x, which is in the purple box up here. Okay? This is another way to solve a system of equations by using inverse matrices. There is a shortcut to find the inverse of a 2 by 2 matrix. It only works for 2 by 2 matrices. Okay? So we're going to let matrix A equal A, B, C, D. All right? Matrix A is invertible if and only if the diagonals, when I multiply the diagonals together, so if I multiply A times D, and then also B times C. So if these diagonals, AD minus BC, does not equal 0, then this matrix is invertible. And this part right here that I have just highlighted or just wrote out, this thing right here that I'm boxing in blue, is called the determinant of a 2 by 2 matrix. Okay, so if AD minus BC does not equal 0, then you can find the inverse, or then the 2 by 2 matrix is invertible, and you can find its inverse by taking the determinant and putting it on the denominator of a fraction, AD minus BC under 1, or 1 over AD, and then multiply. That becomes a scalar, and you're going to multiply it not by A, B, C, D, but what you're going to do is you're going to multiply it by, you're going to switch out the elements on the main diagonal, and so it's going to be a D and an A. And then on the other diagonal, the minor diagonal, you're going to leave the elements where they are, but you're going to negate them. Negative B and negative C. So you can find the inverse matrix of a 2 by 2 matrix by taking 1 over the determinant. That becomes a scalar, and you multiply that scalar by, instead of A, B, C, D, by D, negative B, negative C, A. Practice this by going back to the original problem that we did when we started this video. I gave you the matrix, the 2 by 2 matrix A here, and we found its inverse a couple of different ways. It was negative 3, negative 4, 1, 1. Well, let's do it using the determinant now. So what I'm going to do is I'm going to find the determinant of matrix A. So I'm going to multiply A times D, which is 1 times negative 3, and I'm going to add it, or I'm going to subtract from it the minor, multiplying the minor diagonal, 4 times negative 1. I'm going to put it all under 1. So when I do that, I'm going to get 1 times negative 3 is negative 3, minus a negative 4, so it would be plus 4 under 1. So my determinant is negative 3 plus 4, which is not 0. And it can't be 0 because I can't have 0 in the denominator. It's a 1, so I get 1 over 1. So my scalar is going to be 1 over 1. So I'm going to take my scalar, which, even though you don't really need to do it because it's a 1 right now, I'm going to go ahead and show it to you anyway. So I'm going to multiply that scalar not by A, B, C, D, A, B, C, D, but I'm going to switch the elements on the main diagonal with each other, and I'm going to make it negative 3 and 1, and then I'm going to negate the elements on the minor diagonal, so it's going to become a negative 4 and a positive 1. And when I distribute my scalar through, I end up getting negative 3, negative 4, 1, 1, and that is the same as the inverse. I get the same answer It's just a much simpler process. This only works for the inverse of a 2 by 2 matrix. We will be doing more with the determinant of a matrix next section on Thursday, but I just wanted to show you this because it makes an easy shortcut to finding the inverse of a 2 by 2 matrix, and also finding whether or not it has one. Okay, so this has been a very long video, but I hope it's helpful for you, and I will see you on Thursday.